I have to share the entire desktop then. And you should see it now,
yep.
Right?
Excellent, excellent, yeah.
Okay, thank you. I mean, for introducing me, and good evening to everyone in Australia. Good morning to me and Giulio here in Europe. It's quite early here. And the next few minutes, I'm going to present some new work that I've been doing here in England at the University of East Anglia with Emily Alberello. And this puts together some stuff that Giulio discussed, because we talk about CIs, and some stuff that was discussed earlier in the morning for you and later on last night for me, in the sense that we are using a nonlinear Schrödinger model for water waves. So, okay, yeah, it's moving. Do you see it's going smoothly, the video?
Yes, yes.
Okay, yeah.
Yes.
Perfect. So what we want to model is this condition. This is a video I took when I was on board the South African vessel, the S.A. Gallas, in 2017, in the middle of winter, because of the Southern Hemisphere, so July is middle of winter, in the so-called marginalized zone that Giulio earlier presented. We have those small flows and those big waves that were generated by the storm offside of the ice in the open ocean, and they are propagating in the ice. So that's the problem we want to tackle. Giulio already introduced what's the marginalized zone, and this is part of the broader sea ice zone, which is a seasonal sea ice area around Antarctica that in winter increases to the light shaded area, light blue shaded area, and in summer it recedes to the dark blue due to the breakup. And it's important. And the general definition by Peter Waltons and some other that follow is that the marginalized zone is that area exposed to the open ocean processes, and particularly waves. And this is an area that's important for biogeochemistry and physical processes, and it governs the heat and momentum exchange between the atmosphere and the deeper ocean. So this is a large area. It's about 5 million square kilometers as its maximum. And it's about 20–30% of the total sea ice. So you can imagine how big of a role it plays on the climate system and why we want to study. So in the Southern Ocean, we have waves all year round, and those are generated by the strong winds that are uninterrupted by any continental mass between the 40 degrees south, the roaring 40s, the furious 50s, and the screaming 60s. In the top left plots, you see the winds that are mostly in a clockwise direction for the mean value and the 90th percentile, and there is a strong correlation with the large waves in the bottom panel down here. So we have waves that can exceed on the 90th percentile the 6 meters wave height, but that's the percentile, but the most extreme events can reach 10 meters or more in wave height, as the one we had on the 4th of July. Here you can see the storm approaching the ice edge and impacting the ice edge on the 4th of July. The wave period in general in the Southern Ocean exceeds the 10 seconds. It's usually around the 12 seconds mark. In those conditions, especially in winter when sea ice forms, we have this constant action, so the ice doesn't form as a flat sheet like the one that Giulio presented in the previous presentation, but it forms in the form of these small flows that they don't consolidate because of the wavy condition themselves. Those small flows are in general between 2 and 4 meters, around the 3 meters mark, and are called pancake ice flows. And so their characteristic dimension is much smaller than the characteristic length. And this kind of ice, it's what makes up most of the winter marginalized zone for tens of kilometers on the ocean side. So the standard model that comes, we have a recent review from Michael Malan and collaborators from 2018 on the JGR. The modeling of this kind of ice, it comes from the modeling of waves, in which we take the usual hypothesis of inviscid, compressible, and rotational flow in deep water, And what we do is to add an hypothesis of having an homogeneous ice layer of constant and average properties on top. What happens if we linearize the water wave problem is that the presence of the ice is an additional pressure. I have noise in the background. Do you have all the microphones?
Yeah, it might be some attendees who are not muted.
And so this is an additional pressure term on the dynamic boundary condition that it's expressed here, in which phi is the derivative of the velocity potential and zeta the surface elevation. So the form of the pressure depends on phi and eta, and different models can be formulated for this external pressure on the sea surface. But the important bit is that we get a dispersion relation with the real part that corresponds to the dispersion relation in the open ocean, and the imaginary part that corresponds to the attenuation rate. So this attenuation rate, Ki, is indeed exponential, and this is for each omega, each frequency component. Now, among the various models that Melan proposed, there is one with dependency on the power law with the power 3, omega 3, which also has dependency on the ice thickness, Hi. And this is the one that I'm going to use in the next few slides. Now, I've talked about sea ice. I'll talk now about the nonlinear Schrödinger equation. And also this one comes from the implicit incompressible and rotational flow in deep waters, so the water wave problem. But in this case, we keep the nonlinearity. And it's a standard model to describe the evolution of the wave envelope B, in this case, which is expressed in the figure here by the darker line. So this is an equation for the complex envelope and not the fast oscillation that we observe. And this is the standard equation that is written in space. So for a wave propagating in space. So it's not the standard form, probably. A lot of work has been done adding dissipative or source term to the nonlinear Schrödinger equation. And also in this case, it comes out from adding a pressure term at the free surface boundary condition. In an heuristic way, it corresponds to just adding a dissipative term minus I Ki B on the right-hand side of the equation. In most of the work that has been done in the past, for example, by Diaz and Wu, this dissipation matches the observed viscous decay rate that we observe in the laboratory. So what I did is plugging the dissipation according to Melan, here, into the dissipative nonlinear Schrödinger equation, and I use it to simulate storm waves propagating from the open ocean towards the interior of the marginalized zone. I selected values of significant wave height of 7.3 meters and peak period of 12 seconds, because those correspond broadly to the conditions that we found in the field in 2017. I assign a Gaussian wave spectrum without loss of any generality, and I'm going to study two sea ice conditions corresponding to low and high dissipation, tuning the viscosity parameter, which is the mu parameter up here in the equation. So some simulation details. I'll analyze a domain that's 55 kilometers long, in which the first 5 kilometers present no ice, or you can see the standard nonlinear Schrödinger equation, and the other 50 with ice. With a resolution of 1 meter, domain is periodic, and it's 6,144 seconds. And I advanced the DNLS in space with a Runge-Kutta algorithm, fourth order Runge-Kutta algorithm. And I used the Fourier transform to compute the derivative in, actually the derivative in time, not in space. There is a mistake there. Also, I reevaluate the coefficient of the DNLS at each spatial step. Because I'm dealing with random waves, I do a very inefficient job, like Eric did this morning in his plenary talk, and I'll use Monte Carlo simulations. and it's not any smart technique or anything. And randomize the amplitude according to a Rayleigh distribution and the phases according to a uniform distribution. As parameters are the ice thickness, I keep it 2.3 meters, which is the standard one that we observed in 2017. And I use the ratio between the density of the ice and the salt water as a 0.876, which is a realistic parameter. And the viscosity parameter, don't look too much at the number. There is a factor of 10 between the two of them, but one means that it is low dissipation and the other is high dissipation. Don't focus too much on this number. So the important bit is that there are two dissipation, low and high, and the domain is 55 kilometers, 5 plus 50. And so this is the solution of the simulations. This is a subset, it's not the entire domain, for one of the random cases. So we have a boundary condition defined at x equal to -5 kilometers at the bottom. In this case, it's the same for a left and right plot. Those waves propagate free, according to the nonlinear Schrödinger equation, up to the line where there is the ice edge. And then the dissipation starts with the model that I described before. So on the low dissipation, you can see there is some reduction of the most extreme waves and more, let's say, black as you progress further away from the ice edge. Whether in the high dissipation is much more clearer that there is a clear dissipation of the amplitude of the waves as we progress further into the ice. But still you have some large waves as denoted by the orangey lines. So now if you look at the dissipation here, I plot it as a function of the distance, the normalized wave amplitude. This is in a logarithmic scale because most of the theories say, and most of the literature say it's exponential, so I want to highlight the exponential. And I want you to focus on the dark, thick lines, which is the results of the simulation. The shaded area is the confidence interval for the two. And as you can clearly see, especially for the high dissipation, this is not a straight line. So it's not an exponential dissipation. What do the other lines mean? So, well, the dashed line is the dissipation computed for the peak period of the initial peak, which is kind of tangent to the initial dissipation that we measure. And the other one, the dotted line, is the one from a parameterization derived based on the field data by KOZWaves and presented in the 2020 Annals of Glaciology paper. What's most remarkable, and now I'll explain why I chose the two different values of viscosity. It was to match at the end of the 50 kilometers the amount of energy that the KOZWaves parameterization gives us, so they are more comparable. But if you focus on the high dissipation, because the model is exponential, it means that it underestimates the dissipation in the earlier stage, close to the ice edge, but it overestimates how fast the waves dissipate further into the ice. Now, if you look at the period, we also see a considerable downshift, and particularly for the higher dissipation case. And this comes from the fact that the higher frequency are dissipated way, way faster, but the lower frequency are hardly dissipated. For example, if you focus on the frequency 1.3, you can see that we start from a certain amount of energy and it goes to 0, whereas at 0.7, the amount of energy is almost unaltered as we progress into the sea ice. So this explains to a certain extent why the dissipation is less exponential. So the concurrent downshift of the spectrum means that, for example, if we have a dominant peak that increases by 1.3 times, the associated attenuation at the peak decreases by 2.46 times, assuming the omega to the 3 power. And this is similar to putting a tangent line like the red one that I show here, that I draw here. So you see that it's clearly that the slope of the attenuation changes as we increase the peak period due to the downshift and due to the selective attenuation of the higher frequency. Now, we can use this simulation also to study some of the extreme events in this field. As you can see here, I plot the maximum value for the two cases. We still have some large waves deeper in the ice, but there is this tendency to decrease, similar to the one that we have for the wave amplitude, clearly. But what we want to do is to look at the probability density function. And so if we start from an exponential distribution for the square of the wave amplitude, which is the thicker line, what happens is that at the edge, due to the nonlinearity of the field, we have an increase of the probability of rogue waves, so a departure of the tail of the distribution from the exponential profile. But as we progress further into the ice, so the lighter shades of color, we revert back to the Gaussianity or to the exponential profile. So that's mainly the results that I want to highlight here. And this is kind of clear because the sea ice dissipation dominates over nonlinear mechanism that lead to the formation of the rogue waves, because we are reducing the energy, we are increasing the wave period, and so it means that the nonlinearity parameter, like the BFI, decreases. Sorry. So to summarize this talk, I want to say that I introduce a dissipative nonlinear Schrödinger equation with a frequency-dependent dissipation, which comes from relevant and recent theory for sea ice dissipation. We run some simulations using Monte Carlo approach, and we show what less than exponential decay of the wave amplitude, and we explain it why. And also that we look at the sea ice dissipation, and we show that this dominates over wave nonlinearity. So it's unlikely that we have rogue waves deeper into the sea ice. Thank you very much for the attention, and any question on the topic?
Yeah, thank you very much, Alberto, for an inspiring talk. Okay, so we have time for some questions now.
May I ask a question?
Sure, of course, Yuri. Go ahead.
Okay, yeah. It seems to me that in natural conditions, or maybe in laboratory conditions, it can be realized a situation when the dissipation is relatively small. In this case, the asymptotic solution of this equation can be constructed, right? And did you try to construct approximate analytical solution for the nonlinear Schrödinger equation with small dissipation?
No, I didn't. The equation that I've used, this one, it's a fairly standard approach as reported by many in the literature, in which this kind of dissipation